bring this home so I did a separate piece of paper.
Maybe so.
No, I think
Okay.
sad days.
Very sad days. Alright, cool kids. I need to change this real quick. Oh man, guys, look at this computer. This is a struggle. Yes. I'm here. I'm ready. I want your questions. 7.1. What's it be get confusing? John.
The sections that included 27 and 33.
Okay. Amen. 27 through 33.
I didn't understand what was happening.
Okay, let's start with 27 through 30. Which ones do you guys have specifically?
27, 21, and 33.
Okay, so for 27 and 29, the directions are as follows. Use the series in the original exercises. You're using 21 and 23. And a function that it represents from the indicated exercise to find a power series for f prime. So long story short, it says go back and find its derivative. Okay, so long story short, it says go back and find its derivative. So for numbers 21 and 23, if you guys were to expand that series, so for 27 and 29, help me out, kiddos. This is 10.1. Okay, for number 27, we were looking at 21. What was that series? It was a series from
2 of n, like 2 to the power of n, times x to the power of n.
okay, and it was from 0 to infinity? 1 to infinity. So if we were to go ahead and expand that power series, couldn't we just be plugging and chugging and get like 2x? Yeah, you're good. Thanks, Ben. And then we end up with 4x squared, and then we end up with 8x cubed, etc. Right? So then number 27, literally the directions just say, use the series and the function it represents to find a power series. Well, what function did it end up representing? Did you guys figure it out?
2 over 1 minus 2x squared?
I think it would be 2x over, right? 1 minus 2x?
Oh, I got 2 over 1 minus 2x squared.
I got what John got.
When I derived it.
Oh, when you derived it for number 27?
Oh.
Sorry, I'm just looking at 21.
Oh, 29.
Does that make sense?
Well,
This is F. Is that okay?
I got 1.
I got 1
over 1 minus 2x. Yeah.
Did it start at 0?
I think so. No.
No, it started at 0.
Oh, yeah, it did start at 0.
Oh, okay, that makes way more sense. So I'm missing the beginning. Sorry, guys. I thought it started at 1. So then if it starts at 0, you guys see what I'm changing, right? And you can do 0 power is 1. Okay, that makes way more sense. You guys realize this is just a geometric series, so we're able to say, oh, it's going to be a sub 1 all over 1 minus r, right?
Yeah.
Okay. So then in number 27, it says, take this guy, and then go ahead and figure out f prime. Well, couldn't I just look at this guy and say, okay, the derivative is going to be 2 plus 8x plus 24x squared, etc., right? I could just take it turn by turn and derive each and every one, and then it says, okay, well, what would the function be? Well, we see the function, so the function would end up being, this is to the negative 1 power, so it will be to the negative 2 power, right? Times u prime. Sorry, did I not do the negative 1 power?
No.
Negative 2 power, negative times the negative, thank you, positive. But does that also make sense with, well, it's not geometric anymore. So you're not going to necessarily be able to see the connection besides realizing, hey, the derivative of is the derivative of.
I got that, but then it said, like, the
Oh, we're
answers
supposed
in
to
the
make
back,
this.
turned it into a series, and I didn't know how they went from that to the series.
So we're trying to figure out the nth term. I see x being raised to the nth power, because it's x to the 0, x to the 1, x to the 2, so that's pretty easy. The coefficient gets a bit harder, because we have 2 to the power of n being multiplied by 2? No, by n, right?
Yeah.
2 to the power of n times n. How did I realize that? Because 2 to the n was already there, and then what was coming down to meet it? N. So you think, okay, if I was taking the derivative, the n comes down, so n times 2 to the n times x to the, wait, is it n minus 1?
Yeah.
Oh, Nope, it's just gonna be,
So it's n equals
minus
1 and x to the n minus 1.
yeah, you could start at 1 and make it x to the n minus 1, or you could start at 0 and have to put a plus 1 for everybody. It's easier to start at 1. The reason why you start at 1 is, guys, what happens to the derivative of the first term?
0.
So then you start 1 further in. Then you can go ahead and have 2 to the 1 times 1, x to the 1. 2 to the 2 times 2, because that 2 came down. 2 to the 3 times 3. Does that make sense? Does that kind of help for 29 too, to give direction? Let's go peek at that next section, because then you ended up in a new section of problems, which is the next page. It says, use the series centered out. So we're looking at 21 again, for instance, for number 31. And now we're trying to figure out the power series for the integral. So then, if we were to go the other direction, for number 31. This would be your final language. Okay, now we need to integrate. And I think it's the integral from a to x, is that right? Let's put it down here. Integral from a to x of f of t dt. We would end up with, hopefully you guys saw that be an ln, right? With u being 1 minus 2x. And so then derivative is negative 2, so that'd be negative 1/2 ln of, you guys agree? Yes. Thank you for that. Now is it good? Because derivative would be 1 over u times u prime, negative 2, negative 1/2 cancels out. Okay. So then if we integrate term by term, integrating the original, integral of 1 would be x, integral of that would be x squared, integral of this would be 4x cubed over 3, right? 8x to the 4th over 4. I'll just leave it 8 over 4 for sake of pattern. And then, John, I'm guessing the nth term again, right?
Yeah.
We still technically have our 2 to the n chilling. Like maybe I'll leave him here, it'll be 2x squared over 2. I see 2 to the n chilling up here. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. I see n plus 1, yeah, because this one needs to be 1, then 2, then 3. So n plus 1 in the denominator, which makes sense with my power rule. And then I see x to the n plus 1. So you can think about, for your nth term, it'd be 2 to the n. Maybe that would have been helpful if we had written it out, which I didn't. The nth term would have been 2 to the n and x to the n. Just think x to the n plus 1 all over n plus 1. So you can kind of just use the nth term to integrate, or the nth term, bring down the n, make it n minus 1. This was just a little bit tricky as far as messing with the bounds, because that derivative is 0. But we could have written this the other way. I think it would make more sense as far as seeing how the nth term is helpful. So we could have started at 0. Then we would have had n x to the n minus 1 times 2 to the, I think it's n, because then if you plug in 0, it's just going to be 0. If you plug in 1, it's going to be 2x to the 0. Yeah, that makes sense. So that definitely helps out in the sense that you can just think of integrating or deriving the nth term. Is that cool? Any other like categories of questions on 10.1? Gabby, you okay? 10.1.
Oh, yeah, no, this
That helps, okay. 10.2, let's go there then. 10.2, let's go there. Let me just get a new page. We'll just do 10.1 questions here. Okay, we'll do 10.2 questions here. Unless, of course, the computer doesn't like to work. Okay. All right, what do we got, guys? What do you want me to look at?
26.
26, what else?
27.
27. We don't like the 20s.
Yeah.
24C. 24C. Okay, let's start at 24C and work our way down. Let's see, why it was so cold. It was 4 long ones. Whew. Okay, it'll turn on. 24C. You guys see a power series, right? Looks like a Maclaurin because I don't see x minus 1s, x minus 2s, x minus 3s, true? So for 24C, it says write g of x. Ooh, who is g? Okay, look at letter B. All right, so help me out. On number 24, what was letter B's answer? Who is g of x?
X plus x squared over 2 factorial plus x cubed over 3 factorial.
Yes, okay, sorry, x plus,
X squared
Okay.
over 2 factorial
Keep
plus x cubed over 3 factorial and so on and so forth.
okay, hold on, pause. We have our special Maclaurins, right?
Yeah.
We go to our special Maclaurins. Is there one where the x terms seem to match the factorials on the bottom?
E. E.
This one looks like it, right? Now, hold on. Compare this to what you just told me. Did it start at 1?
No.
Okay, so pause. Couldn't I get x plus x squared over 2 factorial plus x cubed over 3 factorial just by?
Subtraction 1.
Got it.
Thanks, whoever. One of you both know that one. I don't know who it was. I think it was Jason. Thanks, Jason.
Are those special Maclaurins good
Yes.
to know? Yeah. That was 24. I think that was C, right?
No, see.
Okay. Now, you guys had a question on 26. Let's go to it now. Number 26
26, yes.
gives us 2 over 1 minus t squared. So it gives us what looks like a geometric series, kind of, right? A sub 1 over 1 minus r. And it gives us its antiderivative or its accumulator function from 0 to x of that function at the TDT. Letter A says find the first 4 terms and the general term for the Maclaurin series generated by F. Now, hold on, wait. We can fit this in to a pattern, right? Isn't it like 1 over 1 minus x? Okay, so hold on, let's start with, you guys have the series right in front of you, right? Let's start with 1 over 1 minus x. Who is that guy? Geometric, starting at 1 and multiplying x squared every time, right? Okay, so when I have, help me out, 2 over 1 minus t squared?
You're playing with 2.
Okay.
Well,
Multiplying everything,
by 2.
okay.
Ratios t
So we start at 2 and then we're multiplying by t squared every time, right?
squared. 2.
Okay, so 2t squared, right?
2t to the 4th.
2t to the 4th,
2t to the 6th.
good. Okay. So the first 4 terms, and it says also the general term?
No.
Oh,
Yes,
no.
yes.
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 Okay. So general term would just be 2, not to the end, because it's just 2 to the 1, 2 to the 1, 2 to the 1. And then it would be t to the
2n.
2n. Right? Because 2 times 0, 2 times 1, 2 times 2, 2 times 3. Okay, but then the question goes on. It says, all right, once you have the first 4 terms and a general term for the Maclaurin series, excuse me, find the first 4 non-zero terms in the Maclaurin series for G. So hold on, let's get who G is. Huh? Yeah, we just did.
Okay, thank you.
Did you want B also?
Yeah, no, fine, yeah.
Okay.
I just want to know where A stopped.
Yeah. So then for letter B, so we've done the first 4 terms and the 10th term. For B it says get G of x, which is the integral from A to x, 0 to x.
0 to x.
Thank you. Of f of t dt. I think they just said the first 4 terms in the general term, right? We don't even have to worry about the
I
function.
don't think it's the general term. I don't think we
Maybe not, that's even nicer if it doesn't. Just the first 4 oh sweet, alright. So guys, this is the first 4 non-zero terms. Can't I take it term by term and just say integrate that guy?
Yep.
Okay, cool, 2x. Integrate that guy?
Okay.
2x cubed over 3. Why is it an x and not a t?
Because when you take the thing out.
Does that make sense? Yeah. For the first 4 terms, we would keep going. We have
2x to the 5th over 5. 2x to the 7th over 7.
gosh. I'm careful. What am I gonna change? I either have to add something or I have to change something.
Oh, you have to do that.
Either make an approximation or just, right? Is that okay?
I
Oh,
remember
yeah.
Would the H test ever do like something where they take out the 2 and then like do the 2 times x plus x cubed? Or they take out a common factor of all functions?
Not normally on Taylor-Maclaurin's, because it's an infinite. I mean, it could. For instance, if it was something like this one, where it was e to the x minus 1, they could have like a random 2 put in, so it's 2 e to the x. Like they could put it in, but I doubt that they would actually pull it out. I haven't seen it on the multiple choice and long answer. You get to leave it in whatever form you want. 27, I think I heard that one, right?
Yes.
What's going on with him? Ooh, the square root. That's fun. The square root of 1 plus x. The first 4 non-zero terms in a Taylor. It says Taylor, but it's centered at 0, so technically it's Maclaurin. Either way. But the first 4 non-zero terms. And then we have, you guys can keep me on track with the other functions. What do we know about the square root of 1 plus x? Do we? What does that mean? We know nothing as far as having memorized a form that we can plug into, but we still know something. Don't we know where a Taylor comes from? So if we know where a Taylor comes from, what can we do? Nope, it's not 1 over, sorry, it's square root of, right? Now pause. If we could integrate this to be one of our special ones, or derive this to be one of our special ones, maybe we could make it fit. But if worse comes to very, very worse, if we're trying to do, what is it, the first 4 terms?
Yeah.
Can't we always say, oh well.
Oh boy. This is gonna open the world.
How many do I need? Just 3, because remember Taylor starts with f up, right?
Yeah.
So if I'm trying to do the first derivative, wouldn't that be 1/2? The negative 1/2, which is, you find is just 1. Whew, that's nice, right? And I have a negative 1/2, which would be negative 1/4. 3/2, good. Bring down the negative 3/2, which would be positive 3/8, right?
3/8.
Yeah.
1 plus
1 plus
x to the 5.
x to the 5/2. Are we okay?
Yes.
Okay, and then what are we supposed to be plugging in? Center that or around? Yeah, 0. So the first 4 non-zero terms, I'm going to say, okay, f of 0 would be just 1, right? F prime of 0 would be 1/2 times x minus 0, all over 1 factorial, plus f double prime of 0,
1/4.
negative 1/4,
X
times
minus
x minus 0 squared, all over.
2 factorial.
Does that make sense? Then I have 3/8 x cubed, right? All over 3 factorial. Does it say journal term? It's nicer if it doesn't. As you guys are doing that, let me rewrite it to make it a little bit nicer. That'd be minus 1, 4 and 2 makes 8, right? Plus 3 and 2 is 6. Well, the 3's are going to cancel, so that'd be 1/16. No general term? So if worst comes to worst, we don't have a special one. Well, I mean, we can make it. We can always make it. Just we like shortcuts, right? We're in BC. We like shortcuts if we can figure them out. That would be letter A.
Yep.
Okay, what else do we got? Use the results found in part A to find the first 4. Oh, use the results. Hey guys, look. We've made our own formula that now we're going to build on. Because when it says 1 plus x squared, what's the only thing I have to change? Square root of x squared, yeah. So as they come back, it's like, all right, whatever. They made me come up with a new one to use. Okay, cool. So square root of 1 plus x squared is going to equal minus 1/8 plus 1/16 x squared cubed. Remember, power to a power, you multiply.
Yeah.
Cool. Does that make sense?
Yeah.
So even though it wasn't one of our special Maclaurins, they kind of are having us use it like one of our special Maclaurins. We just had to make it. And then last but not least, part C says, find the first 4 non-zero terms in a Taylor series. Ooh. For the function h such that h prime is, come on, you guys know this notation. If h prime is the 1 plus x squared under the square root, what am I doing to get to h? Integrating. Now hold on. Do you guys realize there's something extra.
Yay.
Is that our start?
So we're integrating. But what happens when we integrate from 0 to x of h prime of t dt? What does that actually equal?
H prime.
H of x minus h of 0. You see it? So I'm going to integrate. So true. I'm totally going to integrate, but I have to realize, hold on, this is basically integration is net change in that it's not enough just to take the integral. They're saying that the initial point is something different. So to get h of x, I'm going to need to take my h of 0, which is 5, and add that to, okay, now let's go ahead and integrate term by term. So the integral of x is going to end up being, the integral of x squared over 2 is going to be x cubed over 6, right? The integral of x to the 4th over 8, oops, minus the center. Thank you. I need one more term, right?
Oh.
All over, what is it, 102? Is that right? 42 and then 7? Oh, no, sorry, 112, right?
You know, I'm just gonna do that real quick.
7 times 16. I think I'm right, right? 7 times 16.
Yeah, 11. 11 too. Yeah, 112. I didn't just do it.
Yeah, multiply them. 42. There you go. Okay, cool. That finishes us off, right? You guys okay?
Yeah, this was a lot easier than.
Well, you're getting used to a lot of new stuff, right? And so just like, I mean, you guys aren't above the, oh, new things can confuse us. I mean, you're in BC, and so you know a lot. You're just getting up against the, oh, this is new. Okay, you gotta learn those words, Taylor and McLaurin. Gotta learn the basic formula like we had to use here. You can always go back to the basics of taking derivatives and plugging in. But you also have to get down those special McLaurins, because we can play with those and use those. Realize that sometimes you're deriving term by term, sometimes you're integrating term by term. Just gotta take all that past calculus knowledge and now apply it to something new while getting used to the new vocabulary processes, right? Okay, so we got this, don't worry. But I'm sorry that you were stressed on Friday. But now we're feeling a little bit better, yeah?
Yes.
Okay. So let's go ahead and, you guys were able to finish test corrections?
Yeah.
Mostly?
I had like 4.2.
Okay, if somebody needs to, oh, hey, 26 and 27, I totally forgot I had them right there. Oh well, go team. All right, section 10.3. I guess I could kind of like steal this and put it under 26. That might be pretty for our notes, huh? Copy paste. Lagrange error bound.
Good on you.
Is this the right problem? Yeah, that's the right problem. Yeah, George was a huge fan, not really.
Hi, George.
Hi, George. Love you,
Because he's so
George.
watched.
You're my hero.
It's okay, we'll figure it out.
You're still my president, George.
That
I sound like
hurts.
someone right now.
That hurts a lot. I still love you, though, George.
Maybe not Eileen, but George.
George, if you're watching this.
I think we should make our heritage president serve 4 years, so John should be president for the next 3 months.
I'm okay.
You're okay. In absentia? That'd be fun. Alright, cool kids. We have our endeavor card down. Long story short, if you remember from, which you probably don't, that's okay, I'll remind you, from Thursday. If you remember from Thursday, this is what I would call the worst case scenario. Not that this is the worst case, but this is kind of saying how bad can it get? How bad can the error be? Because we are maximizing, not minimizing this guy. The n plus first derivative. Now, if it was a denominator, maximizing would say the smallest value. But since it's the numerator, maximizing, we're literally finding kind of like the largest error bound possible. But when you guys are reading this paragraph, there's a dilemma with z. There's a big dilemma with z. Okay? The idea behind this is we're trying to figure out the error possible in an approximation that's kind of trying to keep us from going to our calculator. But sometimes, to find the maximum n plus first derivative where it occurs at z, you have to use your calculator. So some people are like, that kind of just negates the whole point of the entire Lagrange error bound. For instance, if we were trying to approximate something like sine of 0.1 or 0.7 or something like that, some sine value. In order to, on that sine value, between where it's centered, which we assume is at 0, and the value, which is 0.7, well, what's the maximum value of sine on that, not sine, it's derivative, sorry, of cosine on that interval? Well, cosine decreases, so the maximum cosine would be at 0, but that one's easy. If I was trying to approximate cosine, there we go. Its derivative is sine, and sine goes up, so sine would be maximized at 0.7. So you'd have to use the sine of 0.7 to estimate the error found in the cosine of 0.7 with the Taylor series. You're like, well, I don't know that any more than I knew that, so what's the point? So this whole paragraph basically just says, okay, in the spirit of the approximation idea, sometimes when we're trying to maximize the n plus first derivative at z, trying to figure out what z it is, or just trying to figure out, okay, I might not know who z is, but I do know the maximum value of the n plus first derivative, we might not be necessarily sticking exactly to the maximum value on a certain awkward interval. We might just be choosing the first known reasonable rational number, the first known one. So instead of using like sine of some weird decimal that we don't know, we might say, well, okay, worst case scenario, we know sine is maximized at 1. We'll use 1 instead of that weird decimal that we don't really know, and the whole point is that we don't know what's going on and we're trying to approximate with this other method. So the idea is, every now and then, if something weird is happening, it might be that we don't know exactly what value to use for the n plus first derivative in a certain interval, so we look outside the interval and say, okay, we'll choose the first known reasonable rational number that we know, because if we try to go using something that we don't know, it kind of negates the whole idea. The AP on these types of questions either gives you something like sine or cosine that we know is maximized at 1 or minimized at -1. Well, we're doing maximized, so at 1. Or it gives you some sort of clue in a table, in a graph, in a chart, which would be like a table. It gives you some sort of clue as to what to do for the n plus first derivative. So it's very rare that you have to figure this out on your own. But in the homework and in the notes, it's going to be a little bit confusing at times, because sometimes, even though we're looking at a certain a to b, the maximum here, it's not a known reasonable rational number, so we look outside that and say, okay, well, what is it? Where is it maximized at a number that I do know? Oh yeah, it says defeat the purpose of the error bound. If we go smaller and if we don't go bigger, then there's no guarantee. Like if we go smaller, then we're not for sure guaranteed that our approximation is going to be okay or not. So once again, just think Lagrange error bound is the worst case scenario. The z is a little bit funny, so we have to play around with the n plus first derivative, that whole maximizing idea. We have this example. Okay, suppose, you're welcome for that noise. We use the first two terms of the Maclaurin series for, hey, isn't he a special one?
Yes!
Okay, so Alan, help me out, you guys should know this. Equals.
X minus x squared plus over 2 plus x cubed over 3 plus
Okay, but hold on, we only want the first two terms.
Oh, never mind.
Okay, good.
That's too good.
Well, find only the first two terms, and we're approximating f of 0.1. So we're approximating ln of 1.1. Does that make sense?
Yeah.
But for ln of 1.1, our x is just 0.1, true? So 0.1 minus 0.1 squared over 2. Find a bound on the error. Now we could go ahead and solve it out for the sake of time. Find a bound on the error by using the alternating series error bound, and the Lagrange error formula. We've done the alternating series one before. We would just look at, do you guys remember? The
Oh,
alternating
S.
series.
It's the S minus S.
Yeah. We would do ln of 1.1 minus my 0.1 minus 0.1 squared all over 2. It makes my Alright. So, we have to do Lagrange tomorrow, but you guys know a lot of people working on today. We got a lot of questions answered. Come in tomorrow ready to go. Sound good?
Hopefully I find my
Yeah, hopefully.
I got halfway through.